So now what we're going to do is look at how you can construct ideals in any ring. The ideals you might construct might be trivial, it's okay, but we're going to go over a process of taking a ring element and constructing an ideal from that. And we've actually already seen this. So let's go back real quick, all the way to the integers. Okay, where are the integers? Here they are. Wow, we've done a lot. Okay, so here what did we do? We took an integer m, and from that integer, we constructed a bunch of different ideals from it. What did we do? We looked at all multiples of m. Cool. Let's look at the example we just did now. Here it is. I think you can convince yourself that an x factors out from this expression. So one might write this as a collection of all polynomial multiples of x, where p is any polynomial. So in other words, we took a polynomial, x, and we looked at all multiples of it. And that's how you get these polynomials without a constant term. It's equivalent to having no constant term, then x factors out. So in this definition, we're going to generalize both of those. So suppose you have a commutative ring. Let me scroll up just a touch here. Suppose you have a commutative ring, R, and you have an element A in R. We're going to require commutative. Otherwise, the definition is just a little bit more complicated, and you can still make a definition, but the majority of our attention is going to focus on commutative case. So to make this definition simple, we're just going to assume our ring's commutative. Then what's our set? Well, we're going to define this parentheses A. So this is the notation for a set, is going to be the set of all multiples of A. And since it's commutative, it doesn't matter if we do the multiples of A on the left or on the right. It's going to be the same thing. So just note this is also the same as A times R, where R is an R. And this is called, this is an ideal, and we'll prove it. But this is called the principal ideal generated by the element A. And when you have if you can show your ideal is somehow generated by a single element like this, you say it's principally generated. So we say that A is principally generated by A. It might be generated by other things, but it's at least generated by A. So you might hear me say principally generated ideal or some version of this, and it all means the same thing. So theorem, suppose R is commutative. I guess we do our theorems in pink or purple, I don't know. Suppose R is commutative, and you have some A and R, then the principal ideal generated by A is in fact an ideal. So it makes sense to, in the definition, to say it's an ideal. Proof. We have to go through the checks. 0, is 0 a multiple of A? Yeah, it's 0 times A. Cool. So 0 is in the ideal. Great. 2, suppose you have two elements in your ideal. We can write x equals, I guess we're doing multiples of R on the left, RA, y equals SA for some RS in R. So what does it mean to be in the ideal generated by A? It means you're multiples of A. It doesn't matter if you write the R on the left or R and the S on the left or the right, because we're commutative. I'm just going to choose to put it in the same form as the definition. Then x plus y is RA plus SA, is R plus S times A, because the distributive law holds. Is that a multiple of A again? Yeah, it's R plus S times A. So that is again in the ideal generated by A. Okay, so it's closed under, oh, I'm missing my gold check marks. It's closed under addition. Now we're going to suppose that R is in R and X is in A. the ideal generated by A, then there exists some, oh, I already used R, so I guess I have to use S. There exists some S in R such that X is SA. And then if we multiply R with X, we get R times SA, which is R times S times A, and that's certainly in the ideal generated by A because it's a multiple of A. So it's closed, well, it absorbs multiplication by R. So what do we conclude from this? This is an ideal. The ideal generated by A is in fact an ideal. All right, so it is an ideal, and as a quick example, mz, these multiples of z's, is better written as parentheses m. The kernel of the evaluation map up top that we did in the previous video is really all multiples of x, so we'd write it like that, and so on. Okay, so this is helpful shorthand for saying, hey, I want to take all multiples of something. And in fact, these are ideals. All right, so in the next video, we're going to look at when is the principal ideal generated by A actually everything.